Here we are for another edition of Science Fun. I'm Brent Huddleston.
And I'm Ashley Sharp. We hope you'll enjoy this episode of Science Fun.
Today we'll be learning more about heat transfer. I hope you'll enjoy our show today.
Thanks.
Welcome to science class, grade 5s. We're going to study some more about convection and heat transfer today. But before we do that, I want to just review one thing. I saw a neat thing on inertia the other day, and I want to show it to you. Anybody remember what inertia is? Can you describe it? Yes, Brad?
It's resistance to movement.
Yeah, that's right, resistance to movement. It's Isaac Newton's second law of physics, that things that are in a certain state of motion or a state of non-motion want to remain in that state, and they resist a change. I have a piece of Lego around here, yeah. Okay, this is, what I have here is just a piece of a ice cream pail. Know what I mean? Cut off ice cream pail. And you cut it into a ring shape, and then you take some little light object like a piece of Lego, and you set it right on top of that ring. Not too difficult, right? Now you take some kind of an object like this broom handle, and what we have to do is give that thing a whack and make the Lego fall into the cup. Now it's not as easy as it looks. Anybody want to try it? Okay, Charlie, come here. Give that ring a whack. With inertia, you should be able to just knock it right out of there, eh? Woo! Holy smokers. It's a good thing we used a plastic cup. I was thinking of using a glass beaker. It's a good thing we didn't, eh? Okay, Charlie, that was a nice try, but we're going to have to let somebody else give it a try. You saw what happened. Lego just went flying. Okay, Robin.
He's gonna whack it.
Is he? Give it a whack. Whoa! Not the cup. I guess I should have pointed out, Robin, you're supposed to hit the ring, not the cup. Oh, yeah, okay. Woo. Okay, thanks, Robin. Somebody else. Hey, it doesn't need to be anywhere near that hard. And see, we better try somebody like Cheryl. Nice, gentle hit. It doesn't take a hard whack. It's just a soft one. Wow. You can see where the Lego went. Straight up in the air, right? Well, that's not it. Thanks, Cheryl. Okay, I better demonstrate. Yeah, I think you guys need a little help. This plastic cup might be a little bit too light. Okay, you ready? It just takes a light hit. See there? It's just an easy light hit. Nothing to it. Oh, well, I could give it a good whack, too, I guess. But you better watch out, because it might fly. Oh. Well, it went in and bounced out, but it went straight down in.
You're
Cheating? Me?
Yeah, you're going right here.
Oh, very observant. That's what we want. Good observation.
Well, you're supposed to hit it.
Okay, Tammy's onto it. If you hit on the outside of this ring, let me just demonstrate what happens. Because of inertia, this part of the ring wants to stay in place. And if you hit right on this side right here, then the ring is going to raise up, which launches the Lego off like a rocket. Do you see what I mean? Big launch there. You see it? See how it goes up? But if you hit on the inside of the ring, because of inertia, this part wants to stay here, and you have a downward effect of the plastic ring. And the Lego, of course, wants to stay in one place. So if you get a downward motion and jerk the ring out, then the Lego falls in. In fact, you can just do it very lightly. Falls right in. But if you hit the outside, Lego goes up. Okay, good. That's enough review of inertia, I think. Let's go on to our lesson for today, which is on the convection process and heat transfer. Let's see, these are supposed to be cold. I need a little more cold water. Brendan, would you get one of those cups right there and just get cold water in it? Bring it up. Add a little food coloring to this water so we can see what's happening here. Last day we did a little experiment where we put warm water on a bottom flask and cold water on a top flask, and we saw how by the principle of convection, the warm water wants to rise up into the cold water and let the cold water come down and take its place. You remember the principle of convection, right? No? Yes? Anyone? Yeah, okay. When the warm water gets heated, the warm molecules go up and the cold water molecules come down and take their place. That's the principle of convection, so that molecules keep taking the place of warm molecules. Now, what we're going to do is to take this warm water and show you the difference between the two. We only showed one example last day, but it's even more dramatic if you show both. What we'll do here, I'll add a little more food color to this. Oh, that's just not dark enough for you, eh? Yeah. Okay, let's see. I don't know if I can grab those. Yeah, they're pretty warm, but not too warm. I think I can still grab them. Ooh, well, they're a little warm. Yikes. Now I need a card. Ryan, would you get me a card from the deck over there on that shelf? Whew. Thank you. Okay, these red ones are hot, right? And last day we took a glass like this, a flask, and put it on top, and the warm water rose up into it, right? Well, today I'd like to do the opposite thing. Show you what happens. What would happen if we take the warm one and we put it on top? What's going to happen? According to, yeah, Brad?
Food coloring will go into the cold.
Okay, you think food coloring will go down into the cold? Okay, let's see. We had a little bit of a blubble there. Why would it stay? Yeah, you have it right. The principle is hot water rises. Well, the hot water has already risen, so to speak, because it's already at the top. It doesn't want to go down. And the only way we could get this to go down would be to make this water even hotter than this water. Then this water would come up and replace the top water. Now, just so you're sure I'm not tricking you, we'll do it the other way so you can see the two examples. In fact, here, let's add a little more color. Let's see. Well, yeah, why not? Green for cold, eh? Red for hot? Ooh, boy, that's a dark one, eh? Okay, now this is the one we did last day, where we had cold on top, and the warm red water comes up and takes its place. Or it starts to move up into there. You can see that happening. Yeah, now this is warm on top again and cold on bottom.
It's going to go up.
Will the cold food coloring come up? That's the question. Why won't that come up?
Because the cold water is not.
Yeah, again, hot water. It doesn't matter if it's colored water or clear water. If this water is warm, it stays up. This water is warm, it stays up. This water is warm down here, and so it's trading places with the cold water, and the food coloring is mixing as it does that. So we're getting a pink color here. Okay, good. In this flask, I have some little pieces of paper that I cut up and left in there overnight so that they would become water-soaked or waterlogged. And you can see that they have all fallen down to the bottom of the flask, and they're resting on the bottom of the flask. And now I'm heating that flask up, hoping that we'll be able to see some of the convection currents. Because as this water gets warm on the bottom, it should start to rise and the cold water come down and take its place. So we should start to see some papers moving in there as that happens. I think this alcohol burner here has a better wick. And we'll try using it. And I'm starting another experiment at the same time. So you should get both of these in your notebooks. After you finish drawing those 3 flasks, showing that warm water always rises, then you can start to draw another flask that's being heated up by an alcohol burner with little bits of paper in it, hoping to see some convection currents. And in this flask, I want to get a little bit of water to boil. I have just about a centimeter of water in that flask, and I want to start it to boil. And I'm going to put a rubber stopper in the top of this flask. It has a little hole through it, so that the water vapor and steam can still escape out of the flask. That's a lot of drawing you have to do today, but it'll be worth it when you see the results of these experiments. Yeah, I just filled the flask full of little bits of paper, and they should start to move as we get convection currents in the water. Okay, I just will explain what I'm doing here. I took a small piece of glass tubing, and I'm pushing it through the hole in that rubber stopper, and then I'm putting a piece of plastic tubing, the same kind of tubing you use on your fish aquarium to pump air into your fish aquarium, and I'm pushing that into the other end, so that what we have is a glass tube sticking out and lots of plastic sticking out on the other end. I want to insert this into this flask that's heating up now. We're starting to see a little steam coming off of that flask. And that steam will have to make its way all the way up this plastic tubing and out the top. And I can see that the whole tubing is starting to steam up and fog up there. We need a bit more of a boil on that flask. We need a bit of a boil. Now we're starting to see some action. Yeah, now we're getting a boil on there. Just needed a little help. And if you're real quiet, you can actually hear the steam coming out of this plastic tubing. You hear that? Okay, that's probably good enough. Now we'll allow that to keep boiling. Brendan, I need another cup just like this one, full of just lukewarm water. Woo! Oh, can you see the smoke coming off of that? Ooh. We even have some water vapor starting to come out of there. What happens is steam pressure builds up in the flask, and it erupts. It's like a volcano or a geyser, and then it cools off a little bit again. And then steam builds up again, and it erupts again. I want to prepare some colored water here so we can see what happens. See, that burner is just not hot enough to keep that boiling by itself. How are we doing, Brendan? Ooh. Boy, now we're getting too much. Woo-woo! A lot of power in steam. Thank you. Oh boy.
I know what you're going to do. You're going to put that tube in the water.
You know what I'm going to do, eh? Well, let's see if I can just lay this plastic tubing down.
Whoa.
Get this flask off of here without dropping it or harming anyone. Watch this. Everybody has to be watching this one carefully. Oh boy, I hope this works. We're gonna, yeah. Brad, would you come hold this in that water?
I told you.
Now I'm going to invert this. Watch out. Watch carefully in that flask. Getting some bubbling and churning. Is it hot?
It's going up. It's going up. And it's going to go up. Because the hot ones.
We're getting some green coming up.
Because the hot ones.
Oh, look at this. What can this be?
It's because the hot
Put it in the other glass now, quickly. Ooh, you missed it. Okay, a lot of air escaped in there. I thought we might run out of water. And as soon as, whoa, it's coming back down now, a siphon effect, eh? Oh boy, well if we're going to have a siphon, we better do it this way.
Do that again.
Ooh. We're getting any siphon action there? Oh yeah, now we're getting a little siphon effect. Well, this wasn't part of the experiment, but it's kind of fun to watch a siphon work anyway. Yeah, that was kind of neat. Now, how can you explain that fountain effect? Mike? Yeah, what created the pressure? True, there's atmospheric pressure that had to push down on the water in this cup to push it up that long tube into the flask. That requires a lot of pressure, which demonstrates, thanks Brad, that there is atmospheric pressure in the room here that would lift that water up that high. But you need something to force that water to lift up like that. We need something else. Well, let me explain it to you. Go ahead, Shannon.
Is it steam?
Well, yeah, it has something to do with that steam. Exactly. Because what happened was in that flask, when we boiled the water in the flask, we studied before about expansion of air. And what happens in the flask is as it's boiling, the air that's in the flask gets forced out because of heat expansion. And because of boiling, we get some water vapor that fills the flask. So the flask is full of water vapor and expanded air. Then once we invert it and place the plastic tube into another container, and the flask starts to cool off, then the water vapor condenses and the air molecules in the flask shrink back down, and you have a vacuum in there, so it sucks the water through the tube up into the flask and fills that void that's in the flask. Okay, let me show you another example of convection, of how heat rises. We have here a little test tube, and I think we'll borrow this flame that's going right here. I want to put some ice in the bottom of this test tube. And I just happen to have some ice right here in this egg carton. These little egg cartons work great for making ice cubes. And I have one here. Okay, ice, come on. Get in there. Okay, ice being sunk down to the bottom of the test tube with a rock. And then we take the test tube and hold it over a flame. Now, water in this test tube is starting to heat up. Where does heated water go, everybody? Yes, and where does the cold water go? Down to the bottom. So if you hold this test tube in this flame, you can actually get the water at the top of the test tube to boil and still have ice at the bottom of the test tube, which is rather unusual because just recently we did an experiment with ice where we put ice water into a beaker and then boiled it, and the temperature of ice water will never rise above freezing until all of the ice is gone, because the ice absorbs all the heat. But in this example, we don't have that because the ice is down below the hot water, and so you can actually get the water to boil up above and still have ice down below. Yes. And let me show you another one that's kind of neat. Where's that screen? Oh, yes. Aha. I need a little candle. Here it is. Boy, we're getting too many things up here. I better get some help and clear some of this off before we do this next one, so that it's not quite so cluttered here.
Hey, grab the other one. Use the alcohol.
Now, this is an ordinary piece of wire mesh. Now, if you can imagine some convection currents, air also heats up in the same way that liquids heat up, by convection. That means that hot air is rising up above this candle and churning around, coming back down to the cooler air is coming back down and getting warmed up, and it rises up above the candle. I'd like to get that flame just a little higher. Maybe I can try it with the small candle while we're waiting for that one to burn down a little. Yeah, that one, see, has a much bigger flame. That's what we want. Now, watch this. Here's the interesting thing. This wire mesh will conduct heat, not by convection, but by conduction. And if we put this wire mesh over the flame, you can see that the flame cannot get through that wire mesh. There are lots of little holes in there. You'd think that flame could go right through the holes, but it can't. Why would that be? Yes?
Because there's not enough, because it's a candle and it's wire and it just won't go through because it's wire.
Well, it could go through there. I'll tell you why it won't go through. The reason it won't go through is not because there isn't enough space, because there's plenty of space between that wire mesh. But the wire takes the heat away so quickly that you can't have a